So in the previous video, we defined what a function is, and we looked at some examples. We talked about the domain and codomain and range of functions. In this video, I want to talk about some special properties that functions can have. And to motivate this, I want to start with a question. When can we kind of flip the direction of the arrows of a function and have that also be a valid function? So here's what I mean. Look at this example up here. This was a function, or just kind of an abstract depiction of a function from some set A to some set B. If I flip all the arrows around so that they point from B to A instead of from A to B, that would not be a valid function from B to A. And why is that? There's two problems, and you might even want to pause the video and see if you can figure out what they are. One problem is, right, that there's these elements of B that don't have any arrows going into them. So if we flipped all the arrows around, they wouldn't have any arrows coming out of them, and that's not allowed. A function has to have an arrow coming out of every single element. The other problem would be this one has two arrows coming into it, and so when we flip them around, we'd have two arrows going out. That's also not allowed, right? Everything in the domain has to have exactly one arrow coming out of it. So basically, we're going to think about defining functions that don't have those particular problems so that we could flip them around. That's going to be kind of our motivation. Okay? So, first definition, a function f from A to B is one-to-one. We also call it injective, or an injection is the noun form. I think your book, at least the edition that I looked at, said injunction, but I think that's just a typo. No one ever calls these injunctions. That doesn't make sense. But you do call them injections. So maybe you've heard the word one-to-one, in high school or something. Professional mathematicians tend to use the word injective. It's just kind of a fancier word, but they mean the same thing. Okay, so what does this mean? If and only if no two different elements of the domain map to the same element of the codomain. Okay, so this was actually I guess this was the problem I said second. So this function here is not injective because these two elements of A both map to the same element of B. So this would not be injective. Okay, it's worth taking this English statement that I made, and we're going to write it. We're going to rewrite it using propositional logic. So this says, when we say no two different elements, we're actually making a statement about, for all elements, something is not true. So I could translate this as for all A1 in A, for all A2 in A. For any A1 I pick and for any A2 that I pick, what should be true? This says no two different elements map to the same element of the codomain. So we could say that as if these two elements are different, then they had better not map to the same element of the codomain. That is, f of A1 should not be equal to f of A2. Okay, or taking the contrapositive, right, this is equivalent. I can say for all A1 in A, for all A2 in A, I flip the direction of the arrow and I negate both of them, and that'll be equivalent. So I can say f A1 equals f of A2 implies A1 equals A2. Okay? That first formulation is seems a little more intuitive to us, that this is what it means, right? That if I have two different things, in my domain, when I go across, they are still different after I apply the function to them. However, right, we know that the contrapositive is equivalent, and this way, it turns out, is much nicer to work with. So if you want to prove that something is injective, we will usually use this form, because it's much nicer to assume that things are equal. You can do a lot more things with that than assuming that some things are not equal. So, if you want to prove that something is injective, you'll say, well, okay, suppose that f of A1 equals f of A2, then I just have to show that that means A1 is equal to A2. Right, and intuitively this says, hey, if there's two things and they end up in the same place, then they must have started in the same place. There's no way that they could have ended up in the same place unless they actually started in the same place. That's what that says. Okay? So we'll use this to prove a function is injective. Now, how would we prove that a function is not injective? So we could, stare hard at this definition and scratch our heads and think about it, but we don't have to do that, because now that we've written it down formally, we can just negate this and use some rules and see what comes out. Okay, so let's do that. And I'll put it up here to prove a function is not injective. Okay, I'm just going to write down this thing here and I'm going to negate it. So I'll say not for all A1 in A, for all A2 in A, f A1 equals f A2, running out of space, implies A1 equals A2. Okay, so we'll use some De Morgan laws, right? So first we can push this not in past the for alls, but they have to flip to exists. Okay, so this is equivalent to exists A1 in A. And you know what? I'm gonna, just to abbreviate, I'm gonna write it like this, where I just write them both A1 and A2. And this really just is an abbreviation for there exists in A1 and there exists in A2. I just combine them both, just to save a little space. Not f A1 equals f A2 implies A1 equals A2. Okay, and this is equivalent to, well, let's see, what should we do next? We can use our implication law to turn this into an or, like not this or this, because then we can use De Morgan again. So A1, A2 in A, not, so f A1 not equal to f A2, or A1 equals A2. Right? I just turned this implies into a not this, or this. Not this or this. And okay, now I can use De Morgan to push this not over the or. So it's going to turn into an and I'm going to negate both sides. So I end up with exists A1 and A2 in A such that f A1 equals f A2 and A1 is not equal to A2. Okay. Again, we probably could have come up with this if we just thought about it, but part of the point is, we don't necessarily have to think about it. We can just apply these rules. So what is this saying? What is this telling us? in order to show that a function f is not injective, what do? Well, you have to find some a1 and a2. You just have to give an example, right? This says there exists some a1 and a2, such that, well, fa1 equals fa2, so the function sends them both to the same place, but they're not equal. And that makes sense, right? That's exactly what was wrong in this picture up here. There exists these two elements of A where they get sent to the same thing over here, but they weren't equal over here. Okay. Okay, so that's what it means for a function to be injective. And a function that is injective, means it doesn't have one of those two problems that we talked about up there. To be clear, this isn't a problem, like it's not, a function can be a valid function and not be injective. It's not necessarily a problem. It was just a problem in the context of what if we wanted to flip that function around to kind of have the backwards version. What do we need for that to be a function? Okay, so let's talk about the other one. All right, so a function f is onto, also called surjective or a surjection. Okay, you know what? Sorry, actually, let's do some examples of talking about functions that are injective before we go on and do that. I'd rather do the examples right away. Okay, so going back to a function being injective, first of all, let's think about these functions that we have over here, and let's think about which of these are injective. Okay, so G is, right, and again, you might want to pause the video and decide for yourself which of these three functions, G, H, and L, which ones are injective. See if you can apply the definition and figure that out. Okay, so G is not injective because there's these two different elements of the domain, diamond and triangle, that both go to the same, the function sends them both to the same place, to 6. Okay, so that is not injective. But we could make a function with this same domain and codomain that is injective, right? If I just say, change this to be 200 instead of 6, then each of those three things in the domain would go to different things in the codomain and it would be injective. How about H? H is injective, and it's actually, I think, instructive to formally prove that. So let's quickly actually write a little proof that H is injective. So, to show H is injective. Okay, so remember, being injective said for all pairs of elements in the domain, if HA equals HB, then A equals B. Or if HA1 equals HA2, A1 equals, then A1 equals A2. So to prove that, we're going to say, so first of all, we'll call them N and M, maybe. I don't know, what did I use in my notes? Sure. We'll say M and N be arbitrary natural numbers. Right, so that's dealing with the for all. And then the next part said if the function applied to those two things is equal, then something else. So we're going to say suppose HM equals HN, then we must show that M equals N. Okay, well, if hm equals hn, we can apply the definition of h. So that means that 2m equals 2n. And if we just divide both sides by 2, we get m equals n. So this is the definition of h. And this is divide both sides by 2. Okay, and we're basically done, because we're not basically done, we are done. Because that's what we needed to show, that m equals n. Okay, and this is a very simple example, because in, if 2m equals 2n, then m equals n. That's pretty clear. There's not much reasoning that needs to happen there, but it's nice to see kind of the form that this kind of proof would take. And again, it exactly corresponds to the form of that, the propositional logic that we wrote out to encode what it means to be injective. Okay, how about our function L? So L is L injective. No, it is not, because, for example, 3 and 6 are two different natural numbers that both get sent to diamond. And in fact, this is like very not injective. There's tons of natural numbers that all go to the same thing. But to prove that it's not injective, all you have to do is give one example, right? The negation said there exists things that are not equal, but they go to the same place. So a valid proof that it's not injective would just be to say, hey, take 3 and 6, they both go to diamond. Done. Okay, but unlike, so with G wasn't injective, but we said, well, if we wanted to, we could sort of fix it by changing, for example, the output for diamond. There's really no way we can fix this one. And it's interesting to think about kind of when that would be the case. But intuitively, there's sort of so many natural numbers and not enough shapes. And no matter what we do, multiple natural numbers are going to have to go to the same shape. Because every natural number has to go to some shape. And there's more than 3 natural numbers, so we're kind of stuck. Okay, so now let's talk about functions being onto. So a function f from a to b is onto or surjective or a surjection if we could say every element of B, the codomain, is covered, or every element of B gets hit or something like that. That is, we could say for all B in our set B, the codomain, there exists some element A of the domain such that FA equals B, right? For any B, we can find at least one A where the function sends that A to that B. Okay? And again, this example function up here is not onto because these B's, these two dots here, they don't have any arrows coming into them, right? They don't get hit by any A, or they're not covered, so to speak. We cannot find some A such that the function f sends A to that B. Okay. So, right, to show that a function is onto, we just have to prove this statement. We, pick an arbitrary B and then show how that we can find an A that makes this work. To show that something is not onto, right, again, we can take the negation and use some equivalences to figure out what we have to show. So, let's see. We use, I'll just combine these steps. We use De Morgan's law twice, or De Morgan's law. I'll push the not over both these quantifiers, and they both are going to flip. And actually, then I'm done, because then it's just not equal to. So I'll have exists some b in B such that for all a in A, f of A is not equal to B. Okay, so this is how we would show that a function is not onto. We have to pick some particular B and show that no matter what A you pick, f will not send that A to that particular B. Okay. Hang on a second. Sorry about that. All right. So let's look at these example functions over here and decide which of them are onto. So G is definitely not onto, right? There's lots of natural numbers that get missed, and there's no way to fix it, right? There's not enough shapes to go around, so I can hit 3 natural numbers at most, and then all the rest are going to be missed, so it can't possibly be onto. H is also not onto, because, for example, any odd natural number is never the output of H. On the other hand, as opposed to G, right, we could fix it if we wanted to. We could have a function with this domain and codomain that is onto. For example, well, I mean, like the function that just returns whatever you input. So h of n equals n. That's going to, every natural number is going to be the output from itself. There's certainly other things that are more fancy that are also onto, and I'll let you think of some. This one, also onto, right? Every shape can be the output of that function. So that is onto. All right. So finally, right, kind of our motivation was, when can we flip a function around and have kind of the backwards version of it? Intuitively, right, we just argued that there were kind of 2 problems preventing, that example from doing that. And we've just sort of said, well, what is a function that doesn't have those problems? So we can now define a function f from A to B, which is both 1-to-1 and onto, is called invertible. We also call it bijective, or a bijection. And in particular, we write f with this superscript -1. This is a function from B to A for the inverse of f. That is, how do we define this? The function defined by, well, f inverse of B is equal to A if and only if f of A equals B. Okay, so it does exactly the opposite of whatever f did. And the fact that this is a well-defined valid function depends on the fact that f is both 1-to-1 and onto, right? Because otherwise, we can't necessarily do this. We can't flip it around. This would not be a valid function. Okay. One last comment. There's kind of this is an unfortunate notation, because usually negative exponents mean like 1 over the positive exponent. Like x to the -2 is 1 over x squared. That's not what this -1 power means. It doesn't mean 1 over f. It means the inverse function of f. It's kind of unfortunate that people picked that same notation, but oh well, that's kind of that's what we have. All right. I think I will stop there for now, and maybe later I'll make another video about kind of how we would go about some different ways we could go about proving a function is a bijection. Usually, of course, you can just prove that it's both one-to-one and onto. There's some other things you could do though, and maybe do a few other examples.